I'm very happy to introduce our speaker today, Dr. Tom Steele from Department of Physics and Engineering Physics of University of Saskatchewan. Tom is not new to SUNY IT. We have had Tom here several times in the past. He has been coming here over the past 12 years for research collaboration, attending our conferences. He has given talks in some of our particle physics conferences here. I have known Tom for a long time. We were both graduated from University of Western Ontario in London, Ontario in Canada. We had the same supervisor, PhD supervisor, late Professor Victor Elias, and we have continued, talking. And Tom has developed his own kind of area of expertise, and I branched into some nearby areas, and we have been writing papers on and off. But most recently, we have kind of discovered an interesting connection, which is more than just a repetition of the, and which is slightly maybe more than minor incremental improvement. And that's what brought Tom here 2 years ago, and then also this time, and we are hoping to get something done. I think for the lecture series, it's a custom that when a speaker comes for research collaboration, it was mentioned to me that if I can show a couple of slides how the work of a speaker relates to mine and what are the type of problems we are going to solve. So I'm going to give you a very brief overview, maybe just 2 slides, and then I give the floor to Tom. If we try to zoom out and see the whole physics at once, we can kind of summarize whatever is going on in the world of physics in this ambitious picture in terms of 2 parameters. One is the distances we are talking about, the phenomena, the range of distances that the natural phenomena occur in them. And another parameter is the energy, the range of energy. So we can kind of zoom out and try to show everything that is taking place in physics in terms of those 2 parameters. And roughly, we can think about this 2-dimensional plane in terms of kind of 4 quadrants. One is our macroscopic world. This is where we live. This is where we drive our car to work, and we, play sports and so on. We have the microscopic world, and the region of physics that deals with, the area of physics that deals with phenomena in this region is known as classical physics. Here we have the relativistic physics, which is the physics of high energetic objects that move with speeds comparable to the speed of light. We have quantum world, and then we have this region which is known as elementary particles and fundamental interactions. History of physics, if you look at the evolution of physics, you can see that historically physics evolved along this diagonal line. Why? Because obviously physics began with phenomena that are directly observable. You try to search for mathematical models for phenomena that you can directly observe. And that, of course, is classical mechanics. Classical mechanics is the foundation of anything that we know about physics. So we have classical mechanics that was developed in its final form. Of course, the history goes back even to astronomy, Kepler's laws, and so on. But then the modern form of classical mechanics that we know in terms of Newton's laws of motion, that is a 17th century subject, followed by electromagnetism. And then toward the late 19th century and the beginning of the 20th century, physics started to push those boundaries and move away from phenomena that have direct observation. There were many here, and please bear in mind that this slide is not meant to be comprehensive. There are just so much in between that going on that would be too ambitious to talk about all of those. But roughly you could say 1900 was the discovery of the quantum nature of light, and then after similarities, the quantum mechanics was born. And quantum mechanics, as we know, is the subject that describes the atomic world. So we have something like the structure of an atom. In the middle, we have this hard core that we now know is called nucleus, surrounded by some number of electrons around that nucleus. And then the progress continued, and then along that diagonal line, the progress continued. These are all Nobel Prizes in physics, and there are many, many more Nobel Prizes between these Nobel Prizes. So this is not meant to be comprehensive. And then we learned about relativistic quantum mechanics, which is the extended version of this subject to the cases that particles are moving very fast. So we have relativistic quantum mechanics. Then people started to understand nuclear physics. So nuclear physics, the story of nuclear physics is that this hard core here, called nucleus, if you look closely, we find that this hard core itself is made of other constituents that we call the nucleons. And nucleons are a combination of protons and neutrons. If you look at the periodic table, as you go through the periodic table, you can see that nuclei are defined in terms of their constituents, in terms of the number of protons and neutrons. Now, the story didn't end there, historically. So if you look at that these guys, they have protons and neutrons, then if you look again closely, then you also find that if you pick a nucleon, either proton or neutron, and look closely, you find that they are made of other particles called quarks. So quarks are one of the building blocks of nature that we know. Up to this time, there is no evidence that quarks are made of anything else. So what you can see here, we have the electrons up here, which are elementary, meaning they are not made of anything else. We have quarks inside protons, inside nucleus, that are elementary. And therefore, in order to understand the physics of this, the physics evolved in that direction. Now, why diagonal? Because the history of physics evolved in the diagonal direction because you cannot go down vertical line. If you want to go to small distances, the price to pay is higher energy. If you want to brake the man of the car, so you have to proceed in the diagonal way. To go to smaller distances, you have to pay the price by adding more energies. So then the elementary particles, or elementary particle physics, started to develop. We knew electrons, we knew quarks, and there are other family, other categories. And there are subjects that, on one hand, if you look at it, if you want to know what is the objective of elementary particle physics, is to understand the nature of forces among elementary particles. These are the fundamental forces that we know today. We have gravitational force, we have electromagnetics. We have two types of forces which are confined in small distances only. We don't see them in our daily life. Like for example, here, when we have protons and neutrons have charge, neutrons are neutral, so what keeps them together? It's very easy to see that there has to be something else going on, because otherwise if you have a bag full of protons, then the electromagnetic tendency is to push them away from each other. So something is keeping them in place. And those forces are nuclear forces. So there are subjects that study the fundamental interactions we have this Nobel Prize 1965, quantum electrodynamics, that describes the interaction of light with fundamental particles, interaction of, well, I should say radiation with fundamental particles. We have quantum chromodynamics, which describes, there are other quantum numbers here. This world is really complicated, is really involved. One cannot really summarize this in a cartoon like this, but just to give you an idea, there are other interactions between them. This theory, QCD, describes the strong interaction among those fundamental building blocks. QED describes the electromagnetic interaction among those fundamental building blocks. And then we have the standard model, which describes the kind of like a combination of electromagnetism and weak nuclear force. That was a Nobel Prize in 1979. And then the progress continued. Most recently, in the Nobel Prize in 2013 was given for the discovery of a mysterious particle that is responsible to generate the mass of fundamental particles. You know, when you say an object has that mass, if you keep breaking that object down, it comes to a point that you cannot break it down any further, the building block. And then the question is, where the mass of that building block comes from? Because our perception of mass is by accumulation. If I give you a brick and I tell you why this brick is massive, then in your mind you say, well, okay, because it's made of such and such, if I break it down, I can make it powder, and then if you just add up whatever mass you see, but there is a process that it cannot go any further. When you hit the building block, then you want to know where the mass of that building block comes from. And that led to this theory in elementary particle physics, which was known from 1979. Actually, this Nobel Prize in 1979 was heavily based on this particle called Higgs, but it was not observed in experiment. We knew that there is a mysterious particle that it theoretically provides a mass, but it was not discovered, and it was discovered in July 2012. So that was a huge discovery in this field, which allows us to understand the evolution. There's a recent, again, breakthrough in this field, the BICEP2 experiment in South Pole, which has confirmed the measurement of gravitational radiation and certain type of detail that people are looking for in that radiation, which comes from Big Bang, and confirms what we call inflationary period. So when the Big Bang happened and you have massive explosion and the world start to cool down and expand, at the time of bang, if you call the time of bang 0, 10 to negative 31 after the bang. So you may say, well, why should I even care about that? The answer to that is the following. There are two small lines that they look parallel. The angle between them is like 0.000001 degrees. So if you look at them, if you draw them on a piece of paper, then they look parallel. And then you see, well, these two are parallel. Why should I even care? Now continue those two lines for 10 miles. And then 0.00000 whatever starts to show up in longer distance. So the Big Bang happened 15 billion years ago, 14 something billion years ago. So that 10 to negative 31 seconds after the bang turns out to play a tremendous amount of role in our present knowledge of universe. This discovery is speculated to be the Nobel Prize in 2014. And there are, other theories that wait for their confirmation, like grand unification, supersymmetry, string theory, and then eventually physics evolved in that direction to reach the scale of Big Bang, to reach the early universe. The type of experiments that are done to confirm these theories are either accelerator-based or cosmological observation. BICEP2 is a cosmological observation. They have sophisticated telescopes, actually about a month and a half or 2 months ago, there was a complete documentary on 60 Minutes about this experiment in South Pole. So you may have seen that already. So the information experiment comes either from accelerator side, or it comes from, from cosmological and astronomy side, or it comes from acceleration. Universe evolved in that direction. History of physics evolved in the opposite direction, because we started from what we see and then we go back and see the type of things that we cannot see. In order to see that evolution, the accelerator, this is the most sophisticated accelerator in current time, which is partly in Switzerland and partly in France. It's called Large Hadron Collider, LHC. And some of, the Higgs was discovered in July 2012 in this accelerator, and there are other speculation right now. It's a very hard time for this field. Supersymmetry awaits experimental confirmation, and early universe, and so on and so forth. I need to give the floor to our speaker. Let me say how our work fits in that big picture. Here is proton or neutron. Proton and neutron belong to a big family of particles called hadrons. Hadrons are made of quarks. And so we have on one hand the fundamental theory for a strong interaction of quarks, which is a combination of weak and strong and electromagnetism. So we have a fundamental theory for these. However, if you hit these bags at moderate energies together, for some mathematical challenges, which actually has been listed as one of the few remaining problems in mathematics of this century that haven't been solved. One of those problems is basically the issue that I'm talking about here. The fact that you know the fundamental theory of these quarks inside these bags, and you cannot extend that fundamental theory to describe the interaction between the bags themselves as opposed to between their constituents, has become a big challenge. And this is the area that I've been very interested in. I've been working in this area for some time. The question is how the fundamental theory, fundamental QCD theory, can be used to describe the interaction of these bags. On one side, we have the physics of those bags, that we call it hadron physics. That's what I have done over the past approximately 17 years. And then Tom, during this time, he has stayed focused on physics of those fundamental quarks, and now we are kind of playing with some ideas how the physics of fundamental QCD can be related to the physics of those hadrons. Tom has a very wide range of work, very impressive range of work. Last year, when this discovery was made, Tom, with his graduate student, they wrote a paper in Physical Review Letters. PRL, in case you don't know, is the highest journal in physics. It's the top, just publishes the breakthroughs. And Tom and his graduate student, they wrote a paper about the mass of Higgs. It was 45 or 125? 125. And he was telling me that right before coming here, he wrote another PRL published in Physical Review Letters about the dark matter. And by the way, the picture you see, all we know about universe turns out to be 4% of what exists in the universe. 96% is not known. It's a combination of dark matter and dark energy. And Tom has been branching into these issues also as well. So I think I talked too much, so I let Tom take over.
For this wonderful introduction to this topic. And I'm very grateful to his hospitality and SUNY IT's hospitality, not only this visit, but over many years, perhaps 12 or 14 years. So what I wanted to do, when Amir asked me to give a talk and said to make it general, but general enough for a broad audience, but specific enough to interest specialists, I was wondering if this was even possible. So I hope that I don't, it's not a disappointment to everyone, that it's too technical for the non-specialists and not technical enough for the specialists. And the other thing is, I'm not sure what your traditions are in this series, but if you like to ask questions as you go, that's fine with me, or if your tradition is to wait to the end, that's also fine with me. So what I'm going to try to do is to talk about symmetry as what I think is one of the most important unifying principles in theoretical physics. And Amir's already talked about this in some sense, or at least has alluded to it. So I'm going to talk a bit about what we mean by symmetry, because what we mean by symmetry in theoretical physics of fundamental interactions is maybe different from your conceptual ideas of what symmetry is. And then I'll go through the same sort of transitions that Amir was describing, from classical systems and the role of symmetries and conservation laws there, to relativistic systems, where space-time symmetry starts to become one of our most important guiding principles for everything we do at these energies. Then to small systems that are non-relativistic. And really I'll talk about some classification principles that emerge there. And then finally quantum relativistic systems and the role of broken symmetries. So it's sort of an irony that symmetry being very important, when we get down to the level of fundamental interactions, it's these broken symmetries that are the most interesting ones. And then the story of the Higgs, and I'll throw in a bit of our work on the Higgs and dark matter right at the end. And I apologize for this yellow. I would love to say I could design that, but it's impossible. So what do we mean by symmetry? So symmetry, of course, has its origins in Greek's symmetria, agreement in dimensions, due proportion, and arrangement. And I think that would describe intuitively what we mean by symmetry when we think about it. And it's really, from a mathematical perspective, I guess, some sort of operation that may leave an object or system unchanged in some way. So if we have this cube, if we imagine sort of the symmetry operations of a cube, and imagine that it doesn't have colors or anything so that we can't distinguish it one face from another, we could imagine rotating this cube by 90 degrees around some axis that goes through the center of the face through the center of another face, and of course that leaves it unchanged. And of course there's many faces of the cube and a symmetry operation around each of those. We could imagine a reflection symmetry where we cut a plane through the center and reflect in that plane. And in fact there would be another rotation symmetry through a diagonal. So those are all very, and we perceive intuitively, of course, that this object has symmetry. Now, so what we're describing here is symmetries of objects or collections of matter, and they could be very complex collections of matter, such as living organisms that have perhaps some sort of high degree of symmetry. But really what we're interested in is the symmetries of the underlying physical principles, not the objects themselves or the collections of matter, but the underlying physical principles that describe matter and its behavior. And really this is, as I said, the key concern of theoretical physics at the fundamental level, and it's what I'll talk about today. So the classical systems are systems that are human scale. They are large, they are heavy, they are slow on the grand scale of physics. So classical mechanics is the physics typically describing motion of human scale objects. And this, of course, as Amir said, we didn't actually collaborate on these slides, so so it's interesting how many of our ideas coalesce. So Newton, of course, was the first to really systematically develop this field in terms of things like forces, velocities, momentum, acceleration. Very foundational concepts. But then roughly, it's interesting about the scale of progress, by the way. So roughly a century later, we have Lagrange, who's recasting Newton in entirely different ways, leading to the ideas of Lagrangian mechanics. And the key concepts here are really energy, different types of energy. Hamilton then recast Lagrange in a couple of different ways. One way is the principle of least action, and the other way is just a reformulation of mechanics called Hamiltonian mechanics. And we use these phrases, and I'm sure many of you in the audience, of course, are familiar with these different descriptions, equivalent descriptions of classical mechanics. So I want to talk a bit about the principle of least action, because this is where a lot of symmetry comes, symmetry ideas start to originate. And the principle of least action is a very abstract but powerful principle for formulating classical mechanics. And it's beautiful because it extends beyond mechanical systems into almost all areas of physics. So we can describe electromagnetic fields and things right down to the fundamental interactions in terms of these types of principles. And the idea is very simple, that the trajectory of a particle, its position in space as a function of time, is that minimizes its action. And the action is said to be the total difference along this path between its kinetic and potential energy. And the way that we think about this is that if this is the actual classical trajectory, that any deviations from this, this classical trajectory would actually increase the value of the action. So some sort of minimization principle is at play. And as I said, this is a very abstract principle. It seems to bear no resemblance to Newton, but in fact it's entirely equivalent reformulation. But it actually embeds in it some very beautiful ideas that lead to conservation laws and the connection to symmetries. Now, conserved quantities are quantities that are constant as a system evolves in time. And so if we can catalog enough of these, then we'll start to develop some very good descriptions of physical phenomena. And familiar examples to you would be conservation of total energy, conservation of momentum, angular momentum, and so on. But other things such as conservation of electric charge would also be examples. Now, Newton's perspective on this would really be these conservation laws are some sort of conspiracy of forces. But there's a very beautiful result from Noether that these conservation laws can be connected to a symmetry of the action. In other words, if they, and there's several different versions of this theorem for different types of systems, but the basic idea is if the action is unchanged under some sort of symmetry operation, then a conserved quantity will result. And so this is a very deep and beautiful connection that all these conservation laws that are so fundamental to describing the behavior of physical systems are somehow deeply rooted in symmetries. And I thought, because I'm in the US, I should talk about an example with baseball. So the basic idea here is that the force of gravity is nearly constant in a small region near the Earth. And so what that means is that there's some sort of position translation symmetry. In other words, the force of gravity at this horizontal location is the same as the force of gravity at this horizontal location. There's nothing that can distinguish between these two places. And as a consequence of this translation symmetry, momentum in the horizontal direction is conserved. Time translation symmetry says that the force of gravity doesn't depend on time. So if we measured the force of gravity now and the force of gravity an hour from now, it would be exactly the same. This time translation symmetry tells us that there's a total energy of the system that is conserved. The sum of the kinetic plus gravitational potential energy. And I've got a little Mathematica simulation here. Hopefully not too elementary, but that's sort of the risk of this whole talk, I guess. So this is just some sort of simulation of the motion of a baseball. So I've got this at a speed that we can readily observe. Now the blue dot, which I'm not sure you can see in the color, is the actual trajectory of the baseball. But this red dot here is the sort of shadow, if you like, of the baseball down onto the ground. And you can see that it's moving at a constant speed. That's showing you that, or helping you visualize, that the momentum in the horizontal direction is constant. So the ball never really stops. It halts its upward motion, but its horizontal motion sort of continues. And actually teaching these conceptual understanding of mechanics, I mean, some of you may teach the force concept inventory and would know that this is very difficult for students to conceptualize. I've overlaid on this, of course, the actual parabolic trajectory, just so that you can guide your eye a little bit. Oops, I guess I should raise this a little bit. And so it's the same thing, but it's helping you visualize the actual trajectory, parabolic trajectory of the baseball. And I guess the final thing is conservation of energy. So I guess this one is going to be the kinetic energy, and that's the energy associated with motion. It drops until because the horizontal speed is constant, its contribution to the energy is constant, but the vertical contribution of velocity is going to change and reaches a minimum when the ball stops its vertical motion. And of course, when it's at its highest point, it will have the maximum gravitational energy. But some of them are conserved. So there's this interchange between gravitational potential and kinetic energy. And Newton would say that's a conspiracy of forces. Noether would say it's a symmetry. Now where am I? Okay, back to here. Go. So I want to switch to relativistic systems. I'm calling these fast and lean. I was going to say fast and light, but I didn't want you to get confused with light, the phenomenon of light. So these are lean, fast machines. So first of all, the key thing is that classical mechanics systems behave independently of relative speed. So in other words, we can translate them in space continuously. This leads to the idea of inertial reference frames, where we have some sort of constant speed between a system and a scientific observer that's trying to infer the behavior of this system. Now, Newtonian relativity predicts very simple rules for relative velocities that are known to be experimentally incorrect. It's something that has to be done either to high precision or at high speed. So it's easiest to see for things that move at high speed, such as light. And this is originally the famous Michelson-Morley experiment. And so what we've got here is some sort of car that's moving away from the wall at a speed u, and then some sort of ball or something that's thrown ahead from this car at some speed v compared to the car. And the Newtonian way of adding these speeds together is just add the speed of the ball to the speed of the car. And this turns out to be experimentally incorrect. It's an approximation true for small speeds. And so the resolution of this experimental observation versus, I guess, our Newtonian intuition was ultimately Einstein's formulation of special relativity. Now, what's embedded in this is an idea of space-time symmetry, which is described by the Lorentz transformations. What they tell you is how space-time events, that means things literally, such as a position in space, and literally things such as a measurement of time, are related between scientists that would have a relative velocity between them. And these are the Lorentz transformations in a particular form. And I describe these to my students as a dictionary that you use to translate events between the language of different reference frames, much like the Rosetta Stone. And this symmetry of physical systems under Lorentz transformations is really the basic principle we use to construct relativistic theories. So if we want to create a relativistic theory of fundamental particles, we start with Lorentz transformations as the guiding principle. So all our viable theories have these Lorentz symmetry as sort of their foundation. And the interesting thing about these Lorentz transformations, notice that the space, x is a space coordinate, gets mixed up partly as space and time gets partly mixed up as time and space. So it leads to the concept of space-time. Oh, my joke you can't see. We have to fix that. Okay, so Dr. Steele finally understands the relationship between time and space. Whoops, that was a mistake.
There's a hook there?
There's a hook? Oh, I see. I took it off the hook. Okay, got it. Okay, so that's my joke of the day. I want to go to something else, which is the gravitational equivalence principle. And this may seem to be disconnected with what I just talked about, which is Lorentz invariance. But it goes back to a very old idea by Galileo, throwing stuff off the Leaning Tower of Pisa. And he observed that all objects respond to gravity in the same way, regardless of their composition. And this has been tested again and again over this intervening centuries. And now we have tests of this equivalence principle to incredible precision. What this means is that gravity is sort of almost undetectable in a way. So if we allow, say me, to free fall in a gravitational field, put me up someplace far, far above the Earth and just drop me. Every molecule in my body responds to gravity in the same way. So if you imagine, say, two molecules, in my body, they're each falling in the same way. So there's nothing that's pulling them apart. So there's nothing that would take, the difference between my head and feet, although there's a small difference due to gravity, that would be a very small effect, and so my head would fall the same rate as my feet. So in a way, what that means is that gravity is actually undetectable. If you have a small enough region of a laboratory, then to any precision that you might measure, you could not detect gravity. So gravity is essentially undetectable in a small region, say a small laboratory that we allow to free fall in a gravitational field. And it's because of this equivalence principle. Say carbon fell at a different rate from hydrogen in a gravitational field, it would start to distort the molecules in my body, and I would feel some sort of effect, right? But that's not the way it is. Now, what this means is that in this free-falling laboratory, it's as if there's no gravity at all. And that means the physics that emerged from Lorentz symmetry are going to be valid. And so what Einstein did, and actually this is maybe Einstein's greatest intellectual achievement. I mean, I've often said that I think special relativity was ready to be discovered. General relativity as a theory of gravity was probably not ready to be discovered. I'm guessing maybe 50 years later if Einstein hadn't thought of this. So I think this is true genius in action. Of course, you've heard the idea that gravity is described as a curved space-time geometry, but the key point is that it's really just a theory that tells you how to connect little patches of Lorentz symmetric flat space to another region of Lorentz symmetric flat space. And patching them together in a global way is the phenomenon we understand as gravity. So there's this deep interconnection that Lorentz symmetry, if we implement it locally in a small region, provides a framework for gravity. So yet another manifestation of symmetry in a fundamental force. Now I want to talk a bit about, I've sort of introduced this idea of a symmetry that's implemented a little bit differently at different places. And I've also introduced the idea of symmetries that are introduced in the same way at different places. And this leads to the concept of global versus local symmetry. So general relativity is the example of this local Lorentz symmetry. We implement it in different ways at different space-time locations. But in contrast to that, we implement global symmetries in the same way at all space-time locations. And it turns out that all theories of fundamental interactions are based on these local symmetries. So I want to now shift to quantum mechanics. This is the world of the small, the lean, and the slow. So what this means is things that are below human scale. It's and at that subhuman scale, we replace quantum mechanics with we replace classical mechanics with quantum mechanics to describe the atom and so on. And the objects involved are way smaller in size and mass than human scale. So things like electrons, which are, well, you know, very, very much lighter than a human, and very much smaller than a human. Now, for quantum mechanics to work, the speeds of these objects must be small compared with light speed. And it leads to this beautiful probabilistic interpretation of matter. So in other words, you can't predict the exact location of an electron, but you can predict the probability of the electron being located at different places. And that's really emerges through something called the wave function, and wave mechanics goes back to Schrödinger. By the way, I just love this picture of Schrödinger. I mean, I would love to be as happy as him on any given day. And I love the way the bow tie is off on the angle and his body is off on this angle. And he's smoking something there. Anyway. So anyway, to be as happy as Schrödinger every day seems to be, would be a good thing. Right, so that's Schrödinger. So how do symmetries emerge in quantum mechanics? The phenomena are very different. And I'm not going to talk about this too much, but one of the important things is that symmetries in quantum systems lead to the idea of degeneracies in energy levels. So most of quantum mechanics is concerned about predicting energy levels, say in a material, perhaps a transistor or something of this sort. So it turns out that often these energy levels, you can have degeneracies, which are multiple distinct possibilities with the same energy, and that has lots of physical implications. So these are typically connected to symmetries, not always, but quite frequently. And in the Hamiltonian formulation of quantum mechanics, we'll have conserved quantities whenever we have operators that commute with the Hamiltonian. And this really has a nice analogy with the Poisson bracket formulation of Hamiltonian mechanics. So there is some connection between the quantum and classical realm at this level. Now we can also formulate Schrödinger's equation using Lagrangian ideas. It's not usually done or taught, but it really can be so. And the amazing thing is that the symmetry of the Lagrangian that would lead to Schrödinger's equation has something called a phase symmetry. So it's a global rotation of the wave function by a phase. And it turns out that this symmetry tells us that probability is conserved in Schrödinger's equation. So we talked about the probabilistic interpretation of quantum mechanics. Well, that's only going to make sense if probability is some sense conserved. And it turns out that this conservation of probability is fundamentally connected to the symmetry of phase invariance. And I've got a Mathematica thing for this. It's a little bit hard to visualize, actually. And the colors are really going to be awful here.
In blue, right?
Yeah, the green was a poor choice. Okay.
It's fine.
Yeah, okay. So what I've got here, I guess in red, this red is, the wave function is a complex quantity, so it has an imaginary part and a real part. And the observable quantity is the probability density, which is the magnitude squared of this. And I know that for the experts this is really sort of trivial, but anyway, it's worth talking about. What I'm going to do is I'm going to animate this wave function as a function of this time parameter tau, but I'm also going to rotate the phase of the wave function. And if I do that, and I forget what this system is, it's some sort of example from my quantum mechanics class, but anyway. So if I rotate the phase, you see the real and imaginary parts, they really sort of they're a bit funky, you know, they go back and forth. But notice that it's not changing the probability density. But what I can do is let this system evolve in time. And so the probability, you know, does this green curve, does this funky little dance, and these pieces do their funky little dance with it. But I can change the phase, and that funky little dance sort of stays the same for the green curve. So that's phase invariance in quantum mechanics. Okay, what do I want to do? Get that down here, back to here. Now, we move to relativistic quantum systems as opposed to the non-relativistic ones. These are small, these are lean, they are fast systems. So, they are like quantum mechanical systems. The objects are much smaller than human scale, but they could be moving near the speed of light. And the realm of this is elementary particles, which include the most fundamental constituents of matter. This is sort of the same thing that Amir was showing. So if we imagine this nucleus here as just some sort of object which lives at the center of the atom, and then we have the electrons bound to the atom, we go inside the atom, we have the protons and the neutrons, and inside the protons and neutrons we have these up and down quarks. And there's some scales here which I won't go into. But the point is, what we're talking about is stuff like these up and down quarks. And the electrons. So the standard model is a very awful phrase. I mean, standard model. This is very prosaic. And so it describes the fundamental interactions of nature. And as Amir said, there's three of them, the strong, electroweak, and gravitational force. The strong force is what binds the nucleus together, so binds neutrons and protons. The electroweak is actually a unification of electromagnetism and the weak interactions. And the weak interactions are the mechanism that underlies radioactive decay. And actually, if you'd asked anybody to guess probably that there was a connection between electromagnetism and radioactivity of the nucleus, I think if you'd asked this question of physicists in the early 1900s, I think you'd have been told it's crazy. But it seems to be so. Now, all these interactions occur through what we call gauge bosons. These are the carriers of the force, or the communicators of forces. And I should have a cartoon. Here it is. So this is actually what we think everything is made of, the entire universe, except for dark matter. So what we've got is quarks. Remember, we talked about up and down. Quarks is making up neutrons and protons, but there's actually 6 of them. They get heavier and heavier, so up, down, they go sort of in a mass hierarchy through the up and down, to the strange, to the charmed, to the bottom, to the top. We have the leptons. The electron and the electron neutrino would be probably the most familiar to you, but there's 3 copies of these to go with these 3 families of quarks, the mu and the mu neutrino, the tau and the tau neutrino. The force carriers, the Z and the W that carry the radioactivity decay force, the weak force, the photon that carries electromagnetism, the gluon that carries the strong nuclear force, and here lurking in the background is the Higgs. And the Higgs is the key to it all. It holds this whole thing together. It's the piece that makes this sort of complete. It's the key, it gives the mass to everything. It looks after the symmetries. It's everything. So how do symmetries start to be in play in the fundamental interactions? Well, first of all, both global and local symmetries are in play, which is interesting. What is even weirder is that the symmetries can be exact, or they can be what we say is spontaneously broken by the vacuum or lowest energy state of the system. And this idea of spontaneous symmetry breaking has sort of 2 manifestations, one for global symmetries and one for local symmetries. And the outcomes are extremely different. The physics that emerges from these is very different. Now it turns out that local symmetries are the guiding principle for all these fundamental interactions. They all have the same form. It's an amazing thing. The strong force is said to be a color symmetry of quarks. It's described mathematically by SU3. And what this means is that the forces between quarks of different colors is independent of the color. And so we can rotate the colors without altering the physical phenomena. And color is just a word to give a human concept to this abstract charge of the quarks. The electroweak interactions are, even though these are amazing, I've spent most of my adult life working on these theories called QCD, electroweak is actually even more interesting. And it's described by a symmetry which is SU2 left, which I'll describe in a bit more, but it only acts on the left-handed parts of particles. And I'll try to explain that to you, but it's a pretty difficult concept to conceptualize. And then there's something called hypercharge. It's very closely related to this quantum mechanics phase symmetry. So here's an example of an unbroken global flavors symmetry. So this goes back to Gell-Mann in 1964, sort of the origins of the quark model. And what was happening at that time was this explosion of discovery of new particles. There were so many being discovered that there was almost a crisis in a way. I mean, can all these things be fundamental? Or is there some classification scheme for all these particles? It was Gell-Mann that brought some order to this, essentially invented the periodic table for the new particles being discovered. The idea is that there's patterns amongst these masses, the masses of the new particles that were being discovered. And they're emerging from a flavor symmetry. What this means is if you have quarks of different flavors or different types, their interactions are symmetric under the strong interactions. And by our quantum mechanics argument, this will lead to a degeneracy, which means that these particles will have the same mass. And so these are the patterns that Gell-Mann started to develop. These are representations of SU3, where the quantum numbers of strangeness and electric charge are sort of categorizing the representation. And more or less, to a pretty good approximation, these have the same mass, or any differences between them can be accounted for in a very simple way. And so there's also patterns of 8 as 10, as well as these patterns of 8. Now, here's where we get to a spontaneously broken symmetry. It's called chiral symmetry. Neveu and Goldstone in the 1960s had this beautiful theorem that if a vacuum state breaks a global symmetry, then the spectrum of this theory will contain a massless particle or massless state for every broken symmetry. And there was a bit of a mystery in Gell-Mann's patterns. Although they work very well, the pions that appear in here are just way too light to satisfy the symmetry principles of Gell-Mann's flavor symmetry. And essentially the answer to this is that the pions are Goldstone bosons of broken chiral symmetry. It makes them anomalously light. They're not perfectly massless because the symmetry is explicitly broken as well as spontaneously broken. So it's a bit of a long story, but essentially the idea is that symmetry breaking explains why these things are light. And Amir is, one of the world's experts on this chiral symmetry. So here we go into the mysteries. It all comes down to some important experimental observations of parity violation in the weak interactions. And parity symmetry is sort of mirror symmetry. So if you can imagine it's like looking at physics in a mirror and seeing if the laws of physics as observed in the mirror are the same as those not in the mirror. Space-time reflection. And the landmark signal came from the K+, that there were two decay modes to states that have different parity. So there's no way that the interaction responsible for this decay can conserve parity if the parity of this final state is different from this final state. And not only was parity violated, but it was violated as much as it could possibly be violated, which really kicked people in the head. It was really hard to understand. And the way that you can see that is that there's only left-handed spin polarizations in decays of pions. And I'll try to explain this, but this could be a little bit technical. So here's the process. And this is a mirror, and this is the mirror reverse process. Or the parity, parity revered. Oh, nice typo. Parity reverse typeless process. Okay, so what's happening here is you probably heard about the spin of elementary particles. We can think about that as a vector which is either parallel or anti-parallel to the muon and the muon neutrino, because these are high energies. So it's a bit of an approximation. So this is called helicity or handedness. So if the spin is anti-aligned with the momentum, this is the momentum, then I always forget that's left-handed or right-handed. It doesn't really matter. That's one-handedness. And if they're aligned in the same way, that's the opposite handedness. Now this is what we observe in nature, that all the time when the pion decays, the spin of the is anti-aligned with the momentum. Always, 100% of the time. Now if we parity reverse this, you can imagine if the electron, if the mirror is here and the muon is going this way, in the mirror it looks like it's going that way. So when I parity reverse the momentum direction, it goes in the opposite way, and the neutrino goes in the opposite way. But it turns out spin is different under parity. It preserves its orientation. So this direction is unchanged. This direction is unchanged. So you see what we've gone is we've gone from this helicity, where the spin and momentum are anti-aligned, to this configuration where they're completely aligned. And the fact that this parity reverse process is never observed in nature means that parity is violated as much as it could be. If nature instead had given us 10%, 90% of them like this, and 10% of them like this, then the parity reverse process would be 10 and 90 the other way. But that's not the way it is. It's all or nothing. So we only see this spin polarization. So that means parity is violated as much as it can possibly be violated. And so the technical way of saying that is the weak interactions are purely left-handed. They only can create left-handed polarizations of leptons. And that's why we put this left with SU2. So why is this connected to the mysteries of mass? In fact, this is the entire mystery. We can't actually understand the weak interactions at a very conceptual level. The reason is that the left-hand nature of the weak interaction is completely incompatible with mass for any particle. Completely incompatible. And not only that, but we have these gauge bosons Z and W that are also observed experimentally to be massive. There's no way in naive constructions of the theories for this to be. And so the question is, how do we explain the origin of mass? If we have this, what seems to be a very good symmetry principle, SU2 left, that describes the weak interactions, well, it's no good if it can't also accommodate mass. And so that's where the Higgs comes to the rescue. So it's responsible for what we say is spontaneous symmetry breaking of this local gauge symmetry. And the Higgs mechanism generates the masses of every known particle, including itself. And maybe this is my most technical slide. The idea is that the Higgs is a field. It's described by this field phi, and it has sort of a potential energy associated with it. So you see that for small values of phi, the potential starts to dip down negative, but for large values of phi, it will be overwhelmed and become positive. So the potential starts off at 0, starts to become negative, and then becomes positive again. And there's some minimum potential energy for the Higgs field someplace in between. and it's given by this ratio of parameters. Now the idea is that this represents the vacuum, it's the lowest energy for the Higgs field, and that will break the symmetry of the interactions. So this symmetry is meant to be represented by this rotation. This is sort of a rotationally symmetric around the axis, and as soon as the Higgs drops down into a particular place, it picks out a single direction and breaks this symmetry. So before July 2012, there was only indirect experimental evidence of the Higgs. There was no direct evidence. By the way, this is a beautiful piece of art. So this is Higgs. And notice that it's got a mirror back here. And remember we talked about parity and mirror symmetry? So if you understand this piece of art, you actually understand everything, almost everything about the weak interactions. And what's back here is sort of a depiction of one of the events in the LHC, which ultimately is discovered the Higgs. So beautiful piece of art. So the Higgs mechanism, what does it do? Maybe this is my most technical slide. All right, the point is that if you have a particle of mass, the left and right-handed pieces of a particle, they're sort of connected to each other or married together by the mass term. So the mass connects left to right. And you can see that this is automatically going to violate any symmetry that involves just the left-handed pieces of the fields, because there's no accompanying partner to sop up the transformation that would be associated with that field. So this just breaks SU2 left. So that's why we say mass is incompatible with SU2 symmetry. Now what happens here, oh, I forgot to say something there. So this mass, if we wrote this in sort of a pictorial language, it's sort of connecting the left and right-handed pieces to each other in a picture like this. Now what the Higgs does is it interacts with basically everything: quarks, neutrinos, leptons, gauge bosons. And you could imagine that if this Higgs had zero momentum, which would mean the Higgs field is a constant, then it would mimic the behavior of mass. And that's my best sort of conceptual description of how the Higgs gives mass to things. I've got some others, but maybe I don't have time. The basic idea is that if we have an interaction, these are called Yukawa interactions that connect the Higgs field to the left-handed piece, the Higgs can sop up the symmetry transformation of the left-handed parts of the field and preserve SU2 symmetry. But if this field becomes constant, it gives you something that looks exactly like a right-left piece that is mass. In other words, the strength of the interaction between the Higgs field and these particles is what gives particles their mass. So the stuff that it has the strongest interaction with the Higgs is going to be the heaviest particles we observe. The things that have very weak interactions, very small interactions with the Higgs, are going to be very light. So this is actually a beautiful thing. It means that if we're hunting for the Higgs, if we want to hunt the Higgs and we want to produce the Higgs, the way to produce the Higgs is through these large interactions with the heaviest particles we know, which is the top quarks. And Higgs gives mass to itself in exactly the same way, simply an analogous interaction. So the LHC is the Higgs discovery machine. I guess, Amir, am I too late? Should I stop or jump quickly?
No.
It's okay. I don't think I have much more.
Okay.
Sorry, folks. So Amir showed you this picture. It's a proton-proton collider. It collides protons with protons. This huge ring superimposed on the human landscape. This is all subterranean, of course. The ring is underground. And it's really built to discover the Higgs. You might ask, why protons? Protons is like a bag of quarks. And so proton-proton colliders are considered discovery machines. It's like throwing a bag of hammers at a bag of hammers. Like imagine a bag of hammers and really get it energetic, them rotating all over. If these two bags of hammers collide, one individual hammer may have a higher energy than another. So by colliding a bag of quarks, which is a proton with a bag of quarks, you're actually probing interactions over a huge range of energy scales. So you can very crudely scan over many decades of energy in a single collision. And that's why you build proton-proton machines. They're very difficult to analyze, very messy, but they're very effective discovery machines. And the LHC and the detectors were designed to really search for the Higgs in a whole variety of models up to a huge range of Higgs masses. And here's what Atlas and CMS, the two collaborations, did. They announced in July 2012, July 4th actually, the discovery of a 125 GeV Higgs. And this is the, this is the money plot, sort of this resonance peak at 125, and this would be one of the events in the detector that would have led to this. So how do you identify the Higgs? Actually, the way that you do it is by measuring something called branching ratios, which is the relative probability of different decay products. So after you produce the Higgs, it's going to decay into something. It's an unstable particle. And the branching ratios sort of tell you which outcome will be observed most frequently. And all I want to do is point out to you that these are all these different branching ratios. Probably means nothing to you. But here's the interesting thing for you to think about, is at 125 GeV, where the Higgs is observed, there's lots of decay channels in play. Somehow nature has chosen a mass for the Higgs where the most wide range of possibilities are happening. It's a mystery, I don't know why, but I think it's important. I don't know, I have a feeling it's important. Nature's trying to tell us something, I think, and we're not quite hearing. And so this is the point I just made. Many different competing decay channels. So, tracking down Higgs. This is my second joke. So this is the backyard snow tracking guide, and so you've got cats and mouse riding a bicycle. This is XKCD, by the way. The Prius, I like this one. And here's the Higgs boson. Yeah, I like Legos too. Anyway, so the Higgs has been seen, but there are lots of open questions. What type of Higgs? Are the branching ratios as we predict them actually observed, and do they contain clues to new physics, or are there other surprises? The LHC is shut down for its energy upgrade. Maybe in 5 years we'll actually know the answer to some of these questions. Okay. I'm not going to spend much time on this, other than to say this is some of our work. And essentially the idea is that there's the only place in the standard model that conformal symmetry, which is scaling symmetry, is broken is by the Higgs part. So the question is whether that's really natural or whether it's just some sort of contrived approach to symmetry breaking. So there was this beautiful idea by Coleman and Weinberg that maybe you should have exact conformal symmetry and let the dynamics of the theory break the symmetry itself. It's a beautiful principle. It addresses some of the problems with the conventional symmetry breaking model, but the problem is that it leads to a Higgs mass which is super light and was ruled out a long, long time ago experimentally. But this is some of our work. We recognize that the large top quark Yukawa coupling, which is because the top quark is so heavy, because the top quark is so heavy, it actually destabilizes this Coleman-Weinberg small Higgs coupling solution. But you have a large coupling solution that exists. And the mass is heavy, but it seems to decrease as you work to higher and higher levels of precision. And so what we did is trying to push this as far as we could. And it turns out that the basic theory, the dominant corrections come from a theory where things are known out to 5-loop order. This would probably surprise the experts, but for the non-experts, I guess it's meaningless. Anyway, what we did is a variety of Patti approximation methods, series convergence methods, and as we go to higher loop, we're getting higher and higher accuracy. And what we found is a beautiful power law convergence to a 225 GeV Higgs mass. So basically, as loop order increases, if you take the log of that loop order prediction of the mass and subtract off 125, you get this perfect power law behavior. Same for the coupling, by the way, and the fact that these are universal sort of suggests to us, they're parallel, suggests to us that we've sort of uncovered some underlying phenomena. And the important thing here is not just not to be right and agree with the 125 GeV Higgs mass, but for it to be testable. And our prediction is that these couplings are larger than in conventional electroweak symmetry breaking. And so as new experiments are devised to calculate the Higgs, to measure the Higgs self-coupling, if there's an anomaly and the coupling is larger than expected, then maybe that means that radiative symmetry breaking is the mechanism. And I think maybe I should stop, huh? No? Yes? Dark matter? 2 slides? Yeah? Okay. Dark matter. So there's a huge body of evidence for matter in the universe that we can't see. And I've only named 2 of them, cosmic microwave background, galactic rotation curves, so sort of the rotation rates of stars at different places from the galactic center, blah, blah, blah. There's probably, I think, 5 philosophically and experimentally independent indications of dark matter. I think there's no doubt that dark matter is out there. And like Amir said, it accounts for basically everything. The atoms, the things that we know, are only about 5%. Most of it is dark energy, which is even weirder, and a lot of it is dark matter, something that we would conceptualize as matter as opposed to energy. This is a big mystery. This is the next frontier, I think, of fundamental physics. And it's called dark matter because it doesn't seem to interact with normal matter. In other words, it doesn't interact with light or give off light, therefore dark. And it has to have been stable in order to persist long enough for galaxies to form. It has to persist even in our current era of the universe. So it's very interesting stuff. Now there's something called the WIMP miracle, weakly interacting massive particle miracle. That if dark matter interacts with ordinary matter very, very weakly through the Higgs interaction, this is called the Higgs portal, then it sort of gives the right scale for what we see cosmologically for its abundance. And so lots of ideas about dark matter and its particle physics origin go back to the weak interactions. So that's why I say the weak interactions are so interesting. They seem to connect to a lot of these basic ideas in the universe. So this is some of our recent work. And the idea is that the dark matter is some sort of extension of the standard model. Scalar means that it has no spin, it's like the Higgs, and singlet means that it doesn't interact with normal matter, so it won't interact directly with the weak interactions. And this is called the Higgs portal interaction. So this S is the dark matter field. It interacts only with the Higgs and through this interaction. And what we've done is taken the idea that we use conformal symmetry as a guiding principle. What it's going to do is protect dark matter from decay. We can't write down an interaction that violates conformal symmetry and, we can't write down an interaction that preserves conformal symmetry and allows dark matter to decay. Now, these models have been studied a lot. Typically what people do is use this Coleman-Weinberg mechanism in the dark sector and then communicate that symmetry breaking to the Higgs sector. We did exactly the opposite. We looked at Coleman-Weinberg in the Higgs sector and keep the symmetry unbroken in the dark sector. And what we got is really a viable range of dark matter mass in cosmological abundance. You've probably heard about some of the dark matter experiments doing direct searches for dark matter. Xenon is one of the big players in these experiments. Xenon essentially rules out dark matter masses less than about 80 on this scale. And this is a busy plot, but these curves here are the cosmological abundance of dark matter. So 100% would give us exactly the amount of dark matter that we need to explain what we see cosmologically and astrophysically. And then we've got different curves ranging down to 10%. And then this curve here is one of the scenarios that we considered. We call this a sequential scenario. And you can see that in the region that experiment is still allowing, we can get maybe 30% or less of the dark matter abundance. But then we've got some what we call dynamical scenarios where the symmetry breaking occurs in one. And this is the PRL, that recent PRL that Amir was just mentioning. Okay, that's it. Thank you. Thank you very much to you for your attendance and attention today, and for SUNY IT for supporting this talk and visit. So thanks.
Are there questions, comments?
Yeah. So what do we need to? What's the next big step that needs to be taken?
Yeah, I think there's 2 or 3 of them. And this is sort of where the sort of macroscopic world and microscopic world start to triangulate on the same sort of questions. So the next step, I think, is the experiments at LHC that are going to be looking for particles that we have not observed. Maybe dark matter can be observed directly in that way. So that's the next big step. I think that the upgrade of the LHC, I've sort of glossed over some of these questions, but even the Higgs mechanism, although it works well, it seems to have some inherent conceptual flaws. So it doesn't seem to have quite the ring of truth that we would expect from a theoretical perspective. Now the possibility is that those conceptual flaws are going to be resolved by some form of new interactions or new particles that we observe at the LHC, including possibly dark matter particles. So that's the next big step. I think most of the particle physics world and the fundamental physics world is waiting to see what's going to happen. The sort of complementary scenario is better and better cosmological and astrophysical measurements that are trying to narrow in on dark matter. So I'd say dark matter is the big question, both from sort of the macroscopic sort of observational perspective, detecting it there, possibly direct detection in dark matter experiments, and maybe direct production and detection in particle physics experiments. So I think those are the next big steps. And I guess, you should be watching for this in the next 5-ish years. I mean, if we don't see something soon, then it's not clear what is really going on. I mean, there'll be a lot of very big questions that are left unanswered.
I have a basic question. You said like protony is made up of UND quarks.
Yes.
So what is the source for that positive charge in the proton?
The quarks themselves are electrically charged. So the up and down quarks, the up has charge 2/3 of the magnitude of the proton charge, and the down has -1/3, so they conspire to give you charge 1. So they are electrically charged. And, the Coulomb repulsion between those is overwhelmed by the strong force between the quarks that binds them together.
What's the role of duality versus symmetry? Is duality conceptually the same thing as symmetry? Or
Well, actually, that's a very nice question. I mean, I haven't even touched on the concept of duality, but duality, at least in the string theory perspectives, which maybe are the ideas that are maybe the most viable right now for describing ultimately the origin of all these interactions, obey some dualities. So I haven't really touched on those, but it's quite possible that those dualities are going to be very important as we, perhaps observe new physics and move into more fundamental realms of interactions.
Find something is missing, you're looking in the wrong area, you're not looking for the dual, for example, in optimization theory.
Oh, I see what you're getting at.
Co-state.
Yeah.
Maybe more observable than.
Yeah. Okay, yeah, I see where this question's going. I mean, that's absolutely an important question in terms of the analysis, the data analysis of these experiments, which I haven't even touched on. So the discovery of the Higgs, I mean, you have to be sure that you're not biasing your observations by looking in a particular region. So the statistical analysis is very, very complex, far beyond anything that I could describe properly and do justice. But it's we're seeing a very mature and refined field of data analysis here, for sure. And those sort of, the duality as you were describing it there is absolutely important in the analysis, to be sure that you're not biasing your statistical analysis.
Well, maybe I have a small thing to ask you. The area of fundamental interactions with all the power of quantum field theory, group theory, and all of that is often perceived by people who are not in that field as to be pure, just for complete theoretical and the quest for knowledge. However, we know that underlying phenomena like spontaneous symmetry breaking are relevant to the modern applications. For example, superconductivity, the physics of graphene, their theoretical models are inspired by some of the works done in elementary particle physics. Do you have a comment to make about that? Because I know that you have, particularly about, for example, graphene, and superconductivity is, of course, the biggest example of spontaneous symmetry breaking. And those are completely relevant to nanoscale developments and nanoscale, like carbon nanotubes. They just one single sheet of carbon, and nowadays the fact that those who are investigating the conductivity of graphene, they rely on some of the theoretical works which is done in elementary particle physics. I think that was something that I intended to put in that introduction, but I forgot. So if you could just make a general comment about that.
I don't know if I can take it much further than you have, Amir, but I guess I would say that the origin of a lot of these ideas of spontaneous symmetry breaking was from materials and condensed matter systems, and they got transplanted into particle physics. So the origin of these ideas and the application is in condensed matter systems, and foundations of our modern technology come from a lot of these ideas. I think I would want to go someplace different with this question, though, and that is things like the LHC. I mean, CERN as an organization gave us the World Wide Web, right? I mean, so the actual the ways that scientists had to collaborate and share information, and the data analysis that comes out of this, the amount of data that comes out is staggering. It can't be analyzed at any one location, so it's sort of pioneering cloud computing at new levels. I mean, new ways of building the LHC pushed our boundaries of technology and engineering. It's pushing the boundaries of the way that people work together, humans work together, and the way they share information. I mean, we sort of get value from these types of searches for knowledge because they're so difficult and require so much level of cooperation at an international scale that I think it pushes us as humans in new directions. And that includes new technologies, really pushing existing technologies to their absolute limits. So there's value to be found in the search itself, perhaps not only in its outcomes and discoveries, but there's value in its search. And we see that value again and again.
And I think there are more engineers working in LHC that
Easily,
physicists.
yes, easily.
So that is
And the engineers and scientists have to figure out new ways of working
Working
together on
together.
this scale. I mean, it's,
Yes.
I think it's
like
really,
STEM,
yeah.
STEM department that we don't have now.
Well,
Yes, yeah.
Yeah, it's more like of knowing your opinion. So Higgs mass, what LHC found, is
Yeah.
already heavier than what predictions used to be. I remember predictions used to be around 119 GeV.
Yeah,
And this is, we are in like 125.6.
Yes,
right?
yeah.
So next page, if we look at, so this is already a little bit beyond standard model. Are we looking at supersymmetry? Are you a SUNY supporter, or are you looking at some
Yeah. I think
multiverse theories, or?
I think I'm agnostic on this question, because the Higgs mass is sort of in an uncomfortable region. It's sort of a bit light for supersymmetry, but it's a little bit, it's just uncomfortable. It's sort of, doesn't seem to really give us a good indication of where we're going next. So I'm not sure it's easy to predict what we're going to see, or so supersymmetry, if it's out there, is certainly very unnatural. So it's hard to know. I mean, we might see supersymmetry, but then we've replaced sort of one unnatural sort of theory with another unnatural theory. So I honestly don't know what's going on. There's puzzles out here for sure, and I don't think I have a particular opinion. The Higgs being a little bit heavier than 119, I don't think is really a fundamental signal that something is wrong. The fact that it's that light, I think, is the interesting thing.
Now the radiative electron symmetry
Yes.
that you were talking
Yes.
about. So we looked at a model where we talked about the Yukawa coupling unifications.
Yeah.
I don't see that happening in your model, though. I mean,
No.
your top Yukawa is-
No. The Yukawas are simply fed in. What drives it all is just the top quark Yukawa. So the top quark has to be heavy enough to destabilize the small coupling solution. So even the bottom is light enough that it wouldn't destabilize it. So there's not really any hierarchy of Yukawas that we have to consider, other than the fact that the Yukawa top is very nearly 1. The coupling is very nearly 1. And we don't try to explain that or have an explanation for it, but it seems to be an important ingredient. So the fact that the top is so heavily and has such a large Yukawa is sort of interesting on its own, and I think that's waiting for some other sort of explanation.
Okay, one last question.
Yeah.
You're talking about chirality, left-right
Yes.
asymmetry.
Yeah.
But there are left-right symmetric models.
Yes. Yeah.
Are their Higgs mechanism very different from standard model Higgs mechanism?
Well, that's an interesting question. I wouldn't say they're fundamentally different, no, but the way they're manifested are going to be slightly different in their details. But it does rely on some sort of symmetry breaking mechanism in the same way. So yes, yeah.
Okay, so those of us who live in the standard model, classic model, time and space, have 1:30 appointments. So part of us are going to peel off, and thank you for the most I've ever learned about physics. Thank you.
Thanks.